So this week we're going to use the chi-squared statistic again for categorical data, so things that are in what's called contingency tables or frequency distributions, however you want to talk about it. I think this book uses the word contingency table. So the tables we're just going to make for counts in the spreadsheets. So the chi-squared statistic is, when you're doing counts, is defined this way. Okay. The degrees of freedom is going to vary in this lesson depending on what you're doing. So for the first test, it's going to be n minus 1, but you have to be careful because it's the number of categories, not the number of samples, right? And then the chi-squared component, which is how you calculate the chi, is the observed minus the expected count squared divided by expected. So if you add all of them up, see how it says all the cells, right? Because the contingency table is when it's in your spreadsheet. You add them up. So we already know the chi-squared model. It's a asymmetrical model. We only need the right tail though for this, because as you count whatever you're counting, the higher the number is less likely. So obviously it's skewed to the right. So those are the ones we particularly care about because they're less likely out there. So if you get a sample that's going to give you a small p-value, you're way out there basically. So the sample has to be random, just like any other ones we've done in the past. The sample size is less than 10% of the population, right? So otherwise, independent dependence as far as selecting, and then you need at least 5 or more expected counts. So the key is expected. So when you make your expected, it just have to be 5 or more. So not the observed, but the expected. So the first of 3 tests is called the chi-squared test for goodness of fit. So that's when you have a single variable for a single sample, basically. So if you have multiple, it's going to be one of the other 2 tests because there's 3 total tests. The other 2 are very similar, but this is the only one where it's a single, basically. So you're basically seeing if it matches a theoretical distribution. Whatever that distribution is, whether it has a name or not is kind of irrelevant. Some of them don't have names. You can just say like it fits the population model, you know what I'm saying, or something like that. So basically, the only alternative when you do the is basically they matches the distribution or it does not match, right? Crap. That should be capital, right? So, but the problem is that only one of them basically doesn't fit. Okay, as to which one, who knows? Doesn't really matter at that point. Okay, let's do a problem here. So let's say we go out and figure out or collect data on high earning executives, and we figure out when they're born. So we have them by sign. So does sign indicate high earning individual? Okay, so basically this is a chi-squared test for goodness of fit, right? All right, bold and blue, blue. Okay, so our hypotheses, whoops, that's double lining on me. Let's undo that. Let's see on the screen for some reason. All right, so the null hypothesis and the alternative hypothesis. All right, style text. The distribution of birth months. I don't know, is it by month or the? Maybe I'm wrong on this. Months for high earning executives is uniformly distributed, meaning either each equally likely, right? So I probably should have said the signs and not the birth months, but oh well. I think it's the same, but I could be wrong on that. I'm not an expert on whatever those things are called. Birth months of a high earning executives is not uniformly distributed, right? So they're all equally likely or they're not, basically. So we assume that they are all equally likely unless we find enough evidence to prove otherwise, essentially, right? Okay, so we're going to take this data and put it into a spreadsheet. Copy. I have one going already. I have tabs 1, 2, and 3. All right, so this will be our first tab. I think we're good. So the count is the observed count. So we can abbreviate this of the observed count. Right? Okay, so we need the expected. So there's a couple ways to go about this. I don't think it'll make a difference either way. Why are these not centered? I don't know. Let's fix that. Okay. So you can do it by days and break it up by 365, you know what I'm saying? Or you can do it in 1/12. I don't think it'll make a large difference because, the months only differ by, 29, 30, and 31 days. So I don't think in this case it'll make much of a difference as far as the outcome goes. So we need the total number. That's what we need first. So what I'm going to do is I'm going to do the sum first. Just equals the sum of these. I don't like this. Okay. So the sum is 256. Okay. So there are 256 samples. So if it was uniform, it would be 1/12 of 256. That would be the expected number of people who are Aries, so those high-earning executives, basically. And it's going to be the same for all of them. It would be different if I broke it down by days and did like January, 31 out of 256 or whatever. Or not 256. Number of days in the year. I said that wrong. I don't think it's going to make much of a difference, to be honest with you. Okay, so we need the component. So we want to center that, bold, yellow, and we'll box this up. Again, you can get to these same things up here also. I'm just right-clicking to get those up. Okay, so get back to our notes. Okay, the component, right, remember, is the chi-squared component, because each one of these is a component. You add them up, you get chi-squared. This is the observed minus the expected squared divided by expected, right? Okay, so equals observed minus expected to the second power divided by, again, look back at the formula, expected, right? Okay, and we'll drag that down. Okay, so we want the sum of that, so equals the sum of all of those. I get 5.09, so that is the chi squared. Right? See if you add them up, because the components added up is the chi squared, basically. All right, so 5.09375. Does that get any? Is that exact? I guess it's exact. Perfect. Okay. Sometimes it's not, but if you go off 5 decimal places, that's more than enough anyways. Okay, so what we want to do... All right, let's make another one, actually. Math type. We want to do... I don't know why this is so bad. Oh, because I was typing text before. We want to do the area equals chi... actually, no. It's going to be chi squared. It's all uppercase in distribution. And we only care about right tail for these categorical data ones, because counting, obviously. So it was 5.09375. 375. And then 12 minus 1. Because again, we had 256 samples, but it's not samples. It's the number of categories minus 1. So format, color, blue. Right? And again, this degrees of freedom, n minus 1, only applies to this particular test. It changes for the two tests. Right? Big thing is categories. I see that people make that mistake all the time. It's the most common mistake I see in the goodness of fit, or GOF ones is the abbreviation you'll see in the book, is they'll do the total number of samples, because that's what they saw in the past, you know what I'm saying, which I understand, but it'll be way, way off, because it becomes more normal as you increase the degrees of freedom. Okay, so you need to go to the spreadsheet now. Alright, so now we're going to the expected, basically. So, or the area, so what am I saying? So chi squared right tail. Okay, so we're going to put this in, comma, 12 minus 1. There we go. Okay. Oh, what did I do wrong there? Oh, I put inverse for some. I clicked the wrong one. I want the, because inverse gives you the actual chi-squared value. We want the area, right? Okay, there we go. So 0.09265. 541, I guess. That's good enough. We don't really need all those, right? So 0.926541 dot dot dot. That is our p value, right? So our p value is greater than alpha, because we're going to assume that that's 0.05 using the Fisher rule, because it doesn't specify in the problem. So since that's the case, it's bigger than that, so we do not reject the null hypothesis, right? Okay, so visually, you got to remember what's happening. Very similar to other hypothesis tests we've done in the past, right? Although this one's a skewed one, right? So we only care about this, right? So this is our chi-squared, right? Which was the 5.09, whatever it was, right? That we found. So this is the critical region, right? And we did our calculation there, and we found that our area is more, right? So it's not in the critical region because it's going to be more area, right? So it failed. So there is not enough evidence to conclude to reject the null hypothesis. We cannot conclude that birth month makes a difference in being a high earning executive, or a predictor maybe. Maybe that's a better way to put it. I'm not exactly happy with the wording I put there, to be honest with you, but it gets the point across that there's not enough evidence. So basically we're going to assume they are uniformly distributed. So that's the basic assumption, as it is actually uniformly distributed. All right, that's the end.